Okay, so question 40. Which of the following pairs are keto-enol tautomers? So this is actually, there are a couple different ways to approach this question. You can either try to figure out what the keto form of an enol might be, or what the enol form of the keto might be, or you can actually, sometimes these questions are a little bit too simple because they don't actually give you enols, or they don't actually give you the keto or the aldehyde version. So let's just look at question A. For this one, we don't actually have an enol, so this guy is not an enol. So because this is not an enol, you can't have a keto-enol tautomer pair between these two. So this is right out. These two are not going to be tautomers. But let's just take this aldehyde and talk about what could the tautomer be of this. What would be the enol tautomer of this guy? So if we were going to go ahead and draw our equilibrium arrows, you would say, okay, you have keto-enol tautomerization, and obviously I'm drawing them the same, but obviously again the aldehyde is going to be way more prevalent when you compare it to the enol version of this guy. And we're going to have two different carbons, carbon yellow and let's say carbon green. So what we can do, just redraw the actual number of carbons. So 1, 2, 3, 4, 5. So that's not going to change. What you're going to do is you'll take your yellow carbon, yellow right here, and green right here, and we're going to reform the double bond between those two. So we had a double bond here before, and the oxygen doesn't actually change position. So if this oxygen begins on the green, it's going to end on the green. So what this is telling us is that we are going to have to make the carbon-oxygen connection between the green and the oxygen. So let's go ahead and do that. So we'll go ahead and put our OH right here, and that's pretty much it. So we've reformed the single carbon-oxygen bond, and we've reformed a carbon-carbon double bond. So these two would be the aldehyde enol tautomer relationship. So this would be the enol version. Okay. So this guy looks good. Okay. So now let's ask ourselves if this is actually an enol. That means if it's an enol, we have to have the hydroxy directly attached to the double bond. So we have a double bond with the hydroxy directly attached. So this is definitely an enol. So that sounds good. And so let's go ahead and do the same thing. Let's label everything. So this is our pink, and this is going to be blue. And so that must mean that this is blue, and this is pink right here, if we're just counting our carbons. And so that means that we will have a keto-enol tautomer if that oxygen 1 doesn't move from a carbon to a carbon and it seems to still be on the same carbon, so that's great. And it also has switched from a single to a double bond. And the only other criteria is that this double bond is no longer double, it's actually a single bond now. So this is definitely the keto tautomer, and it's also the keto tautomer of this enol. So this guy seems to check out. So this is definitely a keto enol tautomer, and we'll have the equilibrium favoring way to the right for the keto. And again, let's just be rigorous up above. Going to have way farther to the left. Okay, and that's it for this question. Very simple, actually.